going to be looking at investigation 4.4, which is using similar triangles. And we're going to be looking at what facts about similar triangles allow you to find the lengths in a very large figure that you would be unable to reach to measure. So this is our focus question. If you need a second, go ahead and pause so you can write it down. We're going to be using similar figures, and if you remember, a similar triangle are triangles that have the exact same shape but a different size. Okay, so similar triangles have the same shape but are usually a different size. You can use the relationship between corresponding parts of a similar triangle to solve measurement problems. So, for example, the diagram below shows a method for calculating the height of an object that is difficult to measure directly. If we place a mirror on a level spot at a convenient distance from the object, back up from the mirror until you can see the reflection at the top of the center of the mirror, the two triangles in the diagram are similar. We can find the object's height using these similar triangles. We know they are similar because of this fact right here. The angles are congruent because the light reflects at the same angles. We know that this angle and this angle are the exact same. Now, having just one congruent angle is not enough to say they are similar. However, both of these triangles are right triangles. So now we have our two congruent corresponding angles, which means these are similar. Since we have two corresponding congruent angles, we know that our third one will also be congruent as well. Okay. So now let's do a couple example problems. Jim and Sue used the mirror method to estimate the height of a traffic light. We know the height from the ground to Jim's eyes is 150 centimeters. The distance from the middle of the mirror to Jim's feet is 100 centimeters. And the distance from the middle of the mirror to the point directly under the traffic signal is 450 centimeters. So let's go ahead and sketch this. So here we have Jim. And we know that the height of Jim's eyes, we know that this is 150 centimeters. We also know the distance from the middle of the mirror to Jim's feet. I'm just going to use this dash as my mirror, but this is 100 centimeters. We also know the distance from the middle of the mirror to the traffic light is 450 centimeters. What we don't know is the height of this traffic light. So now we have our picture. Go ahead and explain how you know the two triangles are similar. Okay, again, we know these two triangles are similar because they're both right triangles, and the angle that reflects off of the mirror is the exact same. So we have two corresponding congruent angles, which automatically makes, again, our third one the same. So both are right triangles. And have one other corresponding angle which means we have two corresponding congruent angles. Which gives us our similar triangles. because they are similar, we can use this fact to help us find the height of the traffic light. So I'm missing the height of my traffic light, so I'm going to be looking at the two corresponding sides that I have, which is the distance from the person to the mirror and the mirror to the traffic light. So I'm going to find my scale factor. And to do this, I'm going to take the 450, because that is the side that I know from the triangle that I'm missing information, and I'm going to divide it by the corresponding side. So I have 450 centimeters divided by 100 centimeters, and this gives me a scale factor of 4.5. So now that I know that, I'm going to find the height of the traffic light. So I'm going to take Jim's height, because that's the corresponding side to the side I'm missing, multiply it by my scale factor, and this will give me the height of the light. So Jim's height was 150 centimeters. Multiply it by 4.5, and this will give me 675 centimeters. So the height of my traffic light up here is 675 centimeters. You can also get another example. Students who use the mirror method to find the height, and we're actually into it's not a traffic light, there's a typo. It's a gym wall / basketball court. So we know the height from the ground to Sue's eyes is 130 centimeters, and the distance from the middle of the mirror to Sue's feet is 100 centimeters, and the distance from the middle of the mirror to the gym wall is 9.5 meters. So please be careful when you're drawing your picture and you're looking at our label. So go ahead, draw your picture and pause the video. Okay, when you have your picture drawn, it should look something like this. Now, we have to have all of our measurements in the same form. So because we have centimeters here and centimeters here, but meters here, I need to transform that meters into centimeters. And I know that there are 100 centimeters in every meter. So if I take 9.5 meters and multiply it by 100, that's going to give me 950 centimeters. So, if you have not already, go ahead, find your scale factor, and then find the height of the basketball net / gym wall. Okay, when you did this, you should have found your scale factor. And my scale factor is, I take my two corresponding sides that I know, the 950 centimeters, and I divide it by the 100 centimeters. And this gives me my scale factor of 9.5. So I know that the big triangle is 9.5 times bigger than my small triangle. So I'm going to take Sue's height, multiply it by my scale factor, get the corresponding side, which is the height of the wall. So Sue's height is 130 centimeters, my scale factor is 9.5, and this gives me the height of the wall, which is 1,235 centimeters. Now, if I wanted to put it back into meters so that it is relating back to the original information, I can divide by 100 and get 4.35 meters. Now, if I'm looking at this, I want to make sure my answer makes sense. So I'm going from the small triangle to my big triangle. So I'm increasing in size, which means my scale factor has to be greater than 1, which is true. If my scale factor was less than 1, it would not make sense. If I'm going from my small triangle to my big triangle, I need to increase. Let's look at another example. We're actually going to be doing 2 more examples. So you can do one in the part C and then one in our main ideas. Our first example, we know that Teresa is 5.7 feet from in here. We also have a T-Rex, and that T-Rex is 31.2 feet from the mirror. We also know the T-Rex is 32 feet tall. We want to know how tall is Teresa. Okay, here is our picture. We have the height of the T-Rex, we have our 2 distances, and we do not know the height of Teresa. So, look at your 2 triangles. Remember, we're going from our big triangle to our small triangle, so take that into consideration. And find the height of Teresa. Okay, for my scale factor, I'm going to take my 2 corresponding sides that I know, which is the 5.7 feet and the 31.2 feet. And to find my scale factor, I have my small triangle, that's the piece I'm missing from, so I'm going to take that side of the 5.7, and I'm going to divide it by my corresponding side, 31.2, and this will give me my scale factor, 0.183, 183,000. Now, my scale factor, I'm going to stop and make sure it makes sense. I'm going from my big triangle to my small triangle, so I'm decreasing in size, which means my scale factor has to be less than 1. I look, my scale factor, yes, is less than 1, so I know I'm on the right track. So, to find the height of Teresa, I'm going to take the corresponding side, the height, so the T-Rex is 32 feet tall, multiply it by my scale factor. This will give me the height of Teresa, who is 5.856 feet tall. Now, again, I'm going to stop to make sure my answer makes sense. Does it make sense for a person to be between 5 feet and 6 feet tall? Yes, it does. If I would have done this the other way, and then my scale factor of 31.2 divided by 5.7, I would have gotten 5.47, which would have been the height of Teresa to be 175.16 feet. Okay. Does this answer make sense? No. Okay. So make sure you realize which way you're going from small to big or big to small. Make sure your scale factor relates to that. Okay, let's do one more example. For this example, we have a spaceship. And this spaceship is 138.7 feet tall. And the spaceship is 146 feet from here. We also have a little boy whose name is Eric, and Eric is 3.8 feet tall. What I want to know is how far is Eric from the mirror? Okay, for those of you that want to check your picture, here's a picture of the similar triangles with Eric and the spaceship. This one's slightly different because we're given the two heights, and here we want to find the distance from Eric to the mirror. However, the process is still the same. So if you have not already, go ahead and find the distance Eric is from the mirror. Okay, to do this, we're going to need to find our scale factor. And we're going to find our scale factor by looking at our two corresponding sides that we know. So we know the height of both Eric and the spaceship. So I'm going to take those, and I'm going to take the height of Eric, because this comes from the triangle that I'm missing the information, and I'm going to divide it by the corresponding height, so 138.7, and this gives me a scale factor of 27 thousandths, so 0.027. Now I'm going to take my scale factor, and I'm going to multiply it by the corresponding side. So here is my corresponding side. It's 146 feet. So 146. Multiply it by my scale factor. And this gives me 3.9 feet. So Eric is 3.9 feet from the mirror. Again, gotta make sure this makes sense. I'm going from my big triangle to my small triangle, so I'm decreasing in size, and 3.9 is a lot smaller than 146.